Good morning, everybody. Welcome to this morning session. My name is Alain Valette, and I will be your obnoxious chairman for the session. So the first speaker is Emmanuel Breuillard from Oxford, and he's going to tell us on the Tits alternative and refinements. Please.
Thank you, Alain. It's a great pleasure for me to be able to give this talk this morning in the memory of Jacques Tits. So I'm going to tell you, so this talk will be mostly a sort of survey presentation of where the main theme will be the Tits alternative, a beautiful theorem proved by Jacques Tits in the early 70s. So it will be a survey. I will present some open questions also during the talk. So, the story starts with free groups. So let me remind you the definition. What's a free group? So if you have two elements A and B in a group, you say that they generate a non-abelian free group. So I will talk only about non-abelian free groups. If they are independent, namely that they don't have any relation together. So if you have a word, you write a word in the free group, so something like this, in two letters, and you say that it's a free group whenever you write a word like this, so there can be inverses, then this word is not the identity in the group. Okay, so then it's a free subgroup of G. All right, so for example, if you look at the commutator word x, y, x inverse, y inverse, then this word, when evaluated at A and B, is non-zero if and only if A and B do not commute. Okay, this is very clear. So the existence of free subgroups inside other ambient groups goes back a long time ago. And one of the most famous examples is due to Hausdorff, who in 1914 proved that the group of rotations of the sphere contains a free subgroup. Okay? So he did this in his book on measure theory at the end in order to establish that you cannot construct a measure that is finitely additive on the sphere. And that will be defined, that will be invariant under rotation, and that would be defined on all subsets of the sphere. Okay, so I'll come back to this in a second. And his example is very simple. So here's an example. Hausdorff's example is slightly different from this one, but same spirit. So you take a rotation of two rotations of the same angle, but with one around x-axis, the other one around the z-axis. And you suppose that the cosine of the angle is a transcendental number. Okay, so then the group generated by A and B is free, and the way Hausdorff proves this is by bare hands. So he computes the words. Okay, so it's going to be it's a long matrix product, a long computation, and what appears in this matrix product is every entry will be a polynomial in cosine of alpha. And he shows, by induction, on the length of the word, that this polynomial does not vanish. And so it's polynomial in cosine alpha. So if cosine alpha is transcendental, then you get a free group. Okay, so then this leads him to show that you have the following well-known called Hausdorff-Banach-Tarski paradox, which is a paradox because this construction of a free group allows you to construct some disjoint, so 4 disjoint subsets of the sphere with the property that, with this property over there, so you have A plus, A inverse, A minus, B plus, B minus, they are disjoint parts of the sphere. And your two elements, your two elements in the free group, A and B, they have the property that A plus union A times A minus already covers the whole sphere. So namely, you can just select 2 of those 4, rotate one of them, and you've covered the sphere. that's completely paradoxical because you have 4 disjoint subsets. So if you think that these subsets may have a measure, then it's as if you had double the space, right? So if you had a measure, left invariant measure, rotation invariant measure on the sphere, then the measure of A plus the measure of A minus would be the whole sphere. But the measure of B plus the measure of B minus would be the measure of the whole sphere. But then they are disjoint, so the measure of the sum would be less than the whole sphere, but it's impossible. Okay, so that's Hausdorff. Okay, so the proof. So okay, so why is it called Banach-Tarski? I think the reason is because of the following proof. So Banach-Tarski really proved this, what I wrote. And Hausdorff proved something slightly less strong. And the idea is the following: so you split the sphere into orbits of your free group. Okay, so you find by the axiom of choice, you find a set of representatives of the orbits of the free group, and then you split each orbit into 4 disjoint sets. The set A plus will be the set of words in the free group that starts with A, B plus a set of words that starts with B, B minus starts with B inverse, A minus starts with A inverse. So that gives you 4 disjoint subset of the free group, and then you just take, for each orbit you split your orbit in 4 parts, and then your A will be the union over all the representatives of that part of the orbit when you decompose it, your free group, in that way. So if the orbit is free, so there is no stabilizer, then this works just on the nose. But if your orbit is not free, so which can happen, for instance, if your point is already on the axis of some element in the free group, because the elements in the free group have axes, there are rotations, so they have axes. So if you do that, then you're in trouble. So this is why I say it does not quite work. You have to remove this countable set of axes. And for each of these orbits that are not free, you need to argue slightly differently. But then this is what Barnard and Tarski did, and they end up to this. So when we are in such a situation, we say that the sphere is paradoxical. It's paradoxical space. And it's paradoxical with 4 pieces. So it's enough to do it with 4 pieces. That's minimum number of pieces you can realize this paradox. Okay. All right. So note that in our situation, clearly, because so here the A plus union A minus, this kind of square union means that it's disjoint. Okay, so disjoint set. And clearly from this property, you see that A will send the complement of A minus inside A plus, and it's going to send the complement of B minus inside B plus. Okay? So this leads us to what's called now the ping-pong lemma. So it's called like this now, but it was reinvented by various people and over the years, and Tits is one of them. So I'll talk about this in a second, but what you see is that whenever you are in such a situation, in fact, when you have a paradoxical decomposition, then there must be a free group lurking around. And so this is the ping-pong lemma. So this is a very abstract, simple combinatorial lemma. Any group, let's say generated by A and B, 2 elements, it acts on some non-empty set X. And suppose you have 4 disjoint sets with the property I just outlined that we had for the sphere in this case. Okay? So A will send the complement of A minus inside A plus, the complement of B minus inside B plus. Okay? Then the conclusion is the group generated by A and B is a free group. Okay? So here's an illustration of what's going on. You have your ambient set X. You have 4 disjoint subsets. Okay? And A has this behavior. It sends B minus B plus inside A plus, and A plus also inside A plus, but you don't know what it does on A minus, okay? Well, then the generated free group Y. Well, let's take this word, for example, okay? And let's see why this word is non-zero in the group, is the identity in the group G. Well, I'm going to start with a point, because my word starts with A minus 2. I'm going to start with a point in B plus, and I'm going to be able to follow the orbit of this point when I apply this word. So I apply A inverse, but B plus is sent to A minus by A inverse. So I'm going to end up in A minus, and then again A minus is stable under A inverse. I'm going to stay in A minus, and then I'm going to be sent to B plus, then to A minus, then to B, then to A plus. So I'm going to end up in A plus. So I started with B plus, I'm going to end up in A plus. But those two are disjoint. So this means that the action is non-trivial. So that's a free, it's okay. And this works for every word, so it's a free group. Okay? Okay, so interestingly, so this idea had been used by Fricke and Klein in the 19th century, who in fact had exhibited a free group before Hausdorff in hyperbolic geometry in PSL2R. But of course, this idea does not work in compact groups because there is no dynamics, so it's hard to exhibit those disjoint sets in a compact group. And we'll see that this is essentially what Tits managed to do somehow. So once you have a free group, there is something very simple you could do to generate many free subgroups. So if you have one free group in your group G, this already means that your group has a property, an interesting property, that it has no identity. So there is no word W with a property that it vanishes on all A, B in the group. Okay? So whenever you have a word, let's say in 2 or k letters, you can form what's called the word map. The word map, so it's a map from G to the K to G. And if you have a free group, then you know that this word map is not the constant map equal to the identity. Okay? So now if you just know that, and you are in an ambient group, which is, for example, a Lie group, or something more general like a Polish group, then you can deduce that actually almost every pair of elements, or almost every k-tuple, will generate a free group. So almost every, either in the sense of Lebesgue measure or Haar measure, or in the bare category sense. Okay? So this is sometimes called the ubiquity of free subgroups. And so I gave an example in the case of the Lie group. So if you have a Lie group, then these word maps are, of course, analytic maps. And the word variety defined by the vanishing of the word equals the identity, it will be an analytic subvariety, so it will have 0 measure. And there are only countably many words. So, the complement of a countable union of such subvarieties will be large, will have full measure, or will be co-meager in the sense of bare. So that's, and any tuple in that complement will generate a free subgroup. Okay. So, for example, the unitary group on an infinite dimensional Hilbert space is like that. Also, the absolute Galois group of Q has this property. And now I come to the Tits alternative. So you see, it's easy to find many free subgroups once you have one, but this kind of argument will never tell you anything about whether or not you have a free subgroup in a given finitely generated subgroup. Okay, it's going to give you, okay, there are many, but it's not going to actually point to one. Okay, this is quite common in mathematics. You can show that things exist, but you cannot put your hand on one example. So Tits managed to prove a wonderful theorem, and this is here the first page of the published paper, or part of the first page. And so, so he showed that so at least here, the first theorem is in characteristic 0. If I have a subgroup of matrices, so GLN over a field of characteristic 0, then either the group contains a free subgroup, or the group is actually virtually solvable, so it has a solvable subgroup of finite index. And in fact, you see, as was mentioned yesterday, Tits would always want to see a theorem hold in every characteristic. So the first thing he says after that is, it's no longer true in the field of characteristics non-zero, and then he goes on, and in theorem 2 is about what happens in characteristic P. But what happens in characteristic P is not so much different, and in fact, here is a statement. Given an arbitrary field, if you assume that the group is finitely generated subgroup, then that's the case. So, namely, either you contain a free subgroup or you're virtually solvable. Okay. So the only thing that can happen in positive characteristic is you could have a locally finite infinite group, like SLN over the algebraic closure of the finite field. So then it's locally finite. This is not virtually solvable, but because it's locally finite, it does not contain a free subgroup. Okay, that's essentially the only reason. Okay, so there's an interesting story that, in fact, Serre told me over dinner yesterday, which is that this theorem was proven on a train going from Paris to somewhere in the Alps for a Bourbaki, colloque Bourbaki. And the three of them apparently were on the train, so Bas, Serre, and Tits were on the train. And Bas and Serre asked this question to Tits in Paris, at the station in Paris, and they had the answer when they step out of the train destination. So, okay, so some remarks. So the first is that this is clearly an alternative. Namely, it's exclusive. It's an exclusive alternative. You cannot have a free subgroup and be solvable. So if you have a solvable subgroup of finite index, and you had a free subgroup, then you would subgroup of finite index in a free subgroup is also a free subgroup. So you would have a non-abelian free subgroup in the solvable group, but a solvable group has an identity, so that's impossible. Okay, and the second remark is that it's fairly special to linear groups, to subgroups of matrices, in the sense that it's not true for an arbitrary group. Okay, so it's well known that there are finitely generated infinite torsion groups. One of the easiest examples is the group by Gupta and Sidki. I think the first example is Golod-Shafarevich, but I didn't mention it. But the easiest example to read is by Gupta and Sidki. It's a subgroup of automorphisms of a binary tree. And it's related to the Grigor-Chou group, which is a famous example of group with intermediate growth. So in fact, a corollary of the Tits alternative, a corollary that is stated in Tits' original paper is that thanks to this theorem, you also have a dichotomy of growth between in finitely generated groups. So there are growth, when the growth of a group is you count the number of different elements that can be represented as words of length n, okay, in terms of n. And it's unknown whether a finitely presented group, for example, an arbitrary one, has either exponential or polynomial growth. But for linear groups, it follows from the Tits alternative that you also have this dichotomy of growth between exponential and polynomial. And the Grigor-Chou group is a famous example where this lies in between, so it has intermediate growth. Other examples are the infinite Burnside groups. That, of course, they are torsion, so they don't contain a free group, but they are non-amenable. They are not virtually solvable in particular. Or Tarski monsters that are very interesting groups, that finitely generated groups that have the property that every proper subgroup is of order P for some P. So these wild pathological groups don't arise in a nice linear setting. This is what Tits tells us. Okay, but the linear groups are not the only world where this alternative holds. And in fact, when Tits proved this theorem, shortly afterwards, in the couple of decades after that, a lot of people try to prove similar theorems in other non-linear settings. So, for example, there is a Tits alternative for the group of automorphisms of the free group, in the mapping class group, or in the group of homeomorphisms of the circle, or as we will hear in the next talk, in the Kremenor groups. Okay, so some ideas about the proof. All right, so the proof begins with a reduction to the case when your group is Zariski dense in a simple algebraic group. Okay, so this is a very basic step that was probably very clear to Tits when he did this. So you just take the Zariski closure and then you use the structure theory for algebraic groups. There is a solvable radical. You can mod out by the solvable radical, and then you end up in a semi-simple group. And because if you have a free group in a quotient, you're already free, so it's enough to look at quotients. So you can reduce to the case when you're simple. And then basically the proof has two steps. There's an arithmetic step, and then there's a geometric step. And the arithmetic step is very smart, and the idea is this is what maybe people who had tried had stumbled on, because if you have the idea of using ping pong to prove to find a free subgroup, and you are, let's say, in SO3 like Hausdorff was, then you're a bit stuck because you don't see how there's no dynamics to exhibit this ping pong behavior. But Tits, in this arithmetic step, he comes up with a very nice idea that if your group is like this, Zariski dense in your simple algebraic group, even if your algebraic group is over the real numbers and you are in a compact group, for example, then you can always find a field embedding, so a Galois automorphism, a field embedding that will take the field generated by the entries of A and B and send it to some local field, so some completion, in such a way that the new elements, sigma A, sigma B, where you take the same matrices but you apply the field automorphism, then these two new matrices will generate an unbounded group. So it will be unbounded, because now you're in a local field. This local field could be R, could be C, but it could be a p-adic field. Okay, and it's unbounded. So now that it's unbounded, you can apply, you can find elements that will have eigenvalues of modulus different from 1. You can take pairs of those elements, and the pairs of a fixed matrix with eigenvalues of modulus different from 1 has a quite clear dynamical behavior on the projective space. So namely, it's going to contract almost every point outside of the characteristic subspace corresponding to the eigenvalues of lesser moduli. It's going to send it very close, when you take high powers, to the eigendirection of the top eigenvalue of top modulus. Okay, and this is where suddenly the ping pong table will show up, because A plus will be kind of a neighborhood of the top eigendirection of A, And A minus would be a neighborhood of the hyperplane corresponding to the lesser, the eigenvalues of smaller modulus. And same for B and B inverse. And then so this is a geometric step. Tits shows that in a certain projective space of a suitable, irreducible finite dimensional representation, you have this behavior, you have this pattern. Okay, and therefore you have a free group. So this is the key idea. So okay. All right. So you see, you need a construction. You cannot just say, all right, there is a free subgroup, therefore there are many. But here you have a construction that gives you a free subgroup from a given set of matrices that generate a finitely generated group. Okay. But this proves that you can find two elements. Okay? If you were given two matrices, A and B, and you would like to know if those two matrices generate a free group on their own, that's a different problem. Okay? So this is called the subgroup freeness problem. And it turns out it can be very difficult to do that, to understand when two given matrices generate a free subgroup, and there are famous examples where we don't know. So here is one. It's an example due to John Bierman. It's a famous one because it's related to braid groups and to the linearity of braid groups. And so John Bierman showed that if you look at the braid group with 4 braids, B4, and the famous Breuillard representation of the braid group, it's still not known whether the Breuillard representation of B4 is faithful. It's known now that braid groups are linear, but this particular representation is still unknown whether it's faithful or not. And in fact, before people know, before we knew that braid groups were linear, it was thought that maybe the Breuillard representation was faithful. And it may still be the case, but we still don't know. But the fact is that the Breuillard representation is faithful if and only if these two matrices that you see here, and they are in GL3 of Q of T, where T is indeterminate, whether these two matrices generate a free subgroup. This is the question. Okay? So, yeah, you can try your luck, but you can try this ping pong method, try to find out, try to identify some valuation and some local field and find neighborhoods, but it's difficult. Difficult to show that you have a disjoint. Then you can apply a version of this ping pong lemma. Anyway, so this goes back to the 70s. It's been around for a while. Another problem. I swapped 1 and 2, but never mind. So the other problem is the Linden-Ullmann problem. This is also an even more striking example. You have the two by two matrices, 1, 1, 1, 1, Q, 0, 1, and you ask, do they generate a free subgroup? So it's easy to see that when Q is bigger than 4, they generate a free subgroup. Because when Q bigger than 4, then, so for example, these two matrices, they will generate a free subgroup, and you can look at the ping pong table is something like this. So you look at P1 of R2, and you can get A plus here, A minus here, B plus here, B minus here. Okay, and anything bigger than 2 here will the same ping pong table. In the projective space, you're going to prove that it's a free group. So Q bigger than 4 because you can conjugate so that B has the same. So I could have taken Q and, yeah, if you can conjugate the matrix so that the entry here and the entry there are the same, and then it becomes bigger than 2. So when Q is bigger than 4, then it's a free group. It's not only a free group, but it's a discrete free group in SL2R. Yeah. But when Q is less than 4, it can be a free group. For example, if Q is a transcendental number, But if Q is rational, we don't know. And the conjecture or the question is whether that maybe they never generate a free subgroup if Q is rational. So, as I said, so when you apply this ping-pong method, then you get that when you apply this ping-pong method, you get a free discrete group. Because the ping-pong is done in some local field, you have some topology. So when you get a discrete free subgroup, okay? And so this is also why in this Linden-Ullmann problem it's difficult, because there doesn't seem to be any way to embed your group when Q is between 0 and is less than 4. It seems difficult to the group generated by these two matrices will not be discrete. It's going to be dense typically. It's actually going to be dense in every p-adic field because the group generated by B generates the integers over the p-adic, so it's going to be not discrete. And over the reals, it's also known that it's not discrete. Okay, so then what do? You don't have your ping pong. It's going to be difficult to prove that you have a free subgroup. But on the other hand, as I showed you before, if you have a free group, then you have ping pong. But it's just that it's may be very difficult to find the A plus and the sets. Okay, they may not be geometric. So. As I said, so the Tits alternative was used, so it was, I didn't say that yet, but I'll say it now. So it was used by Margulis in his proof of the arithmetic of lattices. So actually it's, before Margulis proved the superrigidity theorem, Mostow proved strong rigidity. And strong rigidity is a statement that tells us and allows us to understand lattices or discrete subgroups of finite covolume in semi-simple Lie groups. And a key ingredient, it hasn't been mentioned so far in this conference, but a key ingredient to Mostow's rigidity is the famous theorem of Tits that classifies the spherical buildings in rank at least 3. Okay? So when Margulis proved the superrigidity, which is a generalization of the Mostow rigidity, he did not need the Tits theorem anymore, but he needed the Tits alternative at some point. And he needed the fact that lattices contain a discrete free subgroup. Okay, so I'll just mention at this point interesting development in this recent interesting development in this question, which relates the Linden-Ullmann problem to another conjecture in discrete groups, which is a kind of generalization of Margulis' arithmeticity theorem, which is a conjecture of Greenberg and Shalom that a discrete subgroup of a semi-simple Lie group with dense commensurator, the question is it a lattice? So Margulis tells us that if you have already a lattice and it has dense commensurator, then it has to be arithmetic. The commensurator is So the commensurator is the group that such that of all elements in the ambient group that conjugate your discrete group to a group that's commensurable to your discrete group, namely the intersection has finite index. So So in this setting, then Brody, Fisher, MJ, and Van Limbeck showed that you could answer the Linden-Ullmann problem, namely show that when Q is less than 4, this is not free, provided you knew the Greenberg-Shalom conjecture. So you can either view this as an indication that the Linden-Ullmann problem is correct, or an indication that the Greenberg-Shalom conjecture is not correct. So the idea is that this Linden-Ullmann problem group has a dense commensurator, which is given by the So in fact, what they show is that not only it's not free, but it has finite index in an arithmetic group. which is SL2Z bracket 1 over S, where S is the denominator of Q. Okay, and another related open problem is in this direction is the problem of Yves Benoit, which is surprising that we cannot answer this at the moment. So can you find a discrete free subgroup in the product of SL2 cross SL2 with dense projections to each factor? So it's clear that you can find a free discrete group where with discrete projection to a given factor, you find like these two matrices, for instance. But if you want that they are dense projections, so it's called an irreducible group with dense projection to its factor, and still discrete in the product, that seems difficult. And most constructions, you cannot have all these conditions together. Most constructions that are known. So let's go back to this problem to determine whether or not a given pair of matrices generate a free group. So this is called the subgroup freeness problem, and it's algorithmic problem, decidability problem. Can you find an algorithm that would decide whether, if you give me two matrices, I will, in finite time, it will answer yes or no to the question, do they generate a free subgroup? And surprisingly, no such algorithm is known. So it's a challenge to find one, if there is one, or to prove that there is none. So I would tend to think that there is none, and in fact that the problem is undecidable. So the reason is because there are several problems that are known to be undecidable and are closely related. So one of them is the so-called semigroup freeness problem. So it's the same problem but for free semigroups. Okay, so you give me two matrices in GL3Q, and you ask me, do they generate a free semigroup? So semigroup means I don't take inverses here, just take products. This is undecidable. This is undecidable, and it was shown by these people. They reduce it to the undecidability of the word problem in semigroups, which was proven by Turing in one of his last math papers in the 40s, that the word problem, determining whether finitely presented semigroup has solvable word problem, this is undecidable. And so you can relate this to the subgroup freeness problem. Similar problem is the upper left corner problem, which is something I played around with a student a few years ago. So it asks the following question, now not with semigroups, with groups. So you're given finitely many matrices, and you ask, is it true? So you ask the following question, can you decide whether the group they generate eventually has in a matrix whose upper left corner entry is 0? Okay, so this problem again is undecidable. Okay, so move on. Okay, so now I move on to a statement about the uniformity of the Tits alternative. So Tits, in his theorem, it tells you can find a free subgroup. So you can find two elements that generate a free group inside your non-virtually solvable group, finitely generated group you started with. So I proved some years ago, following initial work of Eskin Moses O and a joint work with Tzari Kelander, I proved that in fact you can find these two free groups, two elements that generate the free group, you can find them so that the words you need to take have bounded length. Okay, so if you give me two matrices, maybe I won't be able to determine whether these two generate a free group, but I'll be able to find a very short word of universally bounded length, depending only on the dimension of the matrix, that will generate a free group. So there are only finitely many possibilities, and one of these finitely many pairs, and one of these pairs will generate a free group. Okay? So a key point here is the independence of the field. So it does not depend on the field. So you see a corollary of this is already a simple corollary, interesting to state, and is non-trivial, is that if your group, if the matrices you start with generate an infinite group, then you will be able to find an element of infinite order in finite time, in bounded time. So you can find a small word which will be of infinite order. Okay. And that follows from the theorem, and it's also kind of one of the main special cases that you need to prove the theorem. And so the proof is constructive, so it gives you an algorithm to actually find the W1, W2, and the proof is a kind of an extension of Tits's argument. It's the same strategy of proof. It's again a ping-pong argument, but you have to choose very carefully the field embedding and to understand how to find these neighborhoods A plus, A inverse, A minus, B, and B plus, B minus. Okay? And so the arithmetic step is the hardest in this proof, and it uses some ingredient from Diophantine geometry. So the so-called height gap theorem, which I prove for this purpose, and says essentially that when you have any finite set of matrices, either it generates a virtually solvable group, or actually you'll be able to find a matrix expressible as a short word in the matrix you started with, which has an eigenvalue which is of height bounded away from 0, so in Weil height. Okay, so that's one refinement of the Tits alternative I wanted to mention. Another one is the topological Tits alternative. So this is the following theorem. So this is about dense subgroups. Okay, so as I said, Tits's construction gives you discrete free groups. So how about dense free subgroups? Okay, and so this is a theorem we proved earlier with Guralnickand, and it also takes the form of an alternative. But now it's with a field with a topology. So you start with a local field, little k, and you look at GL little k, and this is either a real Lie group or a p-adic Lie group, or it's also true in positive characteristic. And then you have the following alternative takes the following form. So you look at the topology is a topology induced by little k. And it says that either the group contains an open solvable subgroup, or it contains a dense free subgroup. Okay, so in particular, a dense subgroup of a Lie group, of semi-simple Lie group, will always contain a pair of elements that generate a dense free subgroup. Okay. Okay, so I need to wrap it up, and so I'll mention quickly another interesting development that followed the Tits alternative and has to do with the Hausdorff-Banach-Tarski paradox. So in a very cute paper, Deling and Sullivan, and then Borel in the same edition of the Enseignement mathématique in 1983, they answered a question of Decker from the 50s, which is a generalization of Hausdorff-Banach-Tarski paradox to an arbitrary dimension. So instead of dimension 2, you look at an arbitrary dimension. Okay? And Deling-Sullivan proved that for every odd n, there is a free subgroup of the rotations that acts freely on the sphere. So to act freely on the sphere so you're not only you're a free group, but it means that every element does not have any fixed point. Okay. And Borel completed this by proving that also for even n, so for even n you cannot act freely because rotations have an axis, but you can do almost as good as acting freely. You could act what's called locally commutatively. So this means that the point stabilizers are commutative. Okay? And this is an interesting condition because Decker in the 50s proved that locally commutative free groups, if you have a locally commutative free group, and that's very general, acting on an arbitrary set, then your set is full paradoxical. Namely, you can decompose, you can have a paradox, just as in the first slide, with just 4 pieces. And not only that, but it's actually if and only if, so it's the same. Okay. All right. So as a consequence, the spheres in any dimension is paradoxical, full paradoxical. And and to prove this, they use the Tits alternative. And so the Link-Sullivan, the idea is they do as follows. They realize SON plus 1R as a form of a division algebra over a suitable number field. And because it's a division algebra over a number field, then the elements of a division algebra that are not equal to 1, they don't have 1 as an eigenvalue. Okay? So that's what you need to show, that you know 1 as an eigenvalue, because you want to show that it's free. If it's not free, there is an eigendirection, so there's 1 as an eigenvalue. Okay, so that's how they show there's this division algebra, and this division algebra, the group of units of the division algebra is non-virtually solvable. So by Tits, it contains a free subgroup, and clearly any element there does not have 1 as an eigenvalue, so it acts freely. Okay, so that's the idea. And Borel just used also the Tits alternative in the case when n is even, n plus 1 is odd, and then you can realize the n plus 1, then you can realize SO3 as acting irreducibly in SON plus 1, and you take a free subgroup of dense free subgroup of SO3, given by Hausdorff or by Tits, and then this leads to the proof. So Borel, not only, this is a small remark, but it does give the general conclusion, but Borel did not just prove this. His paper is very beautiful. He proved a very nice theorem about word maps. So he proved that word maps in semi-simple algebraic groups, so this should be a blackboard bold G here for the word map, the word maps are dominant. Okay? So not only are they non-constant, but they're actually dominant. So this means the image is Zariski dense. Okay? So it's a very, very useful thing to know. And I'll end up with, this will be my last slide, almost. If you want to find a group that's locally commutative, so being locally commutative means that point stabilizers are commutative. But something stronger property is what we call the strongly dense property. And a group is strongly dense if every non-abelian subgroup is Zariski dense. Okay? So namely, so this means if you intersect your group with a proper algebraic subgroup, then the intersection with the proper algebraic subgroup of your free group will be a cyclic subgroup of the free group. Okay? So if you have such a free group, which is strongly dense, then of course it acts locally commutatively on any homogeneous space of G, and in particular it will be 4 paradoxical. And so in joint work with Green, Guralnickand and Tao, about 10 years ago, we proved that G of K contains a strongly dense free subgroup, provided K is large enough, so we needed the infinite transcendence degree, or something large, like with the complex numbers it works, for example. But we needed this in characteristic P2 because we had an application to expanders, to finite groups, to the geometry of finite groups, when we proved that there are expanders when the field goes to infinity. So being an expander it's a property of a Cayley graph that means roughly that the Cayley graph looks a little bit like a random graph. Okay, But this theorem here is just for, it just says you can find a strongly dense free subgroup. So in a sense, it's more akin to this ubiquity of free group problem, and that's how we prove the theorem. We show that for any two pair, W1, W2 of any two pair in the free group, two words that don't commute, then typically the image of W1 and W2 of an arbitrary generic pair AB will generate a Zariski dense group. So of course, if you knew that the couple, the double word map W1, W2 were dominant, this would be obvious, but it's not the case. Usually pairs are not dominant. We don't know actually how to characterize pairs that are dominant. But we nevertheless managed to show this and end up with a conjecture which would be a strongly dense Tits alternative. So you would like to prove, like Tits did, that any finitely generated group has a free subgroup, which is not only free, but actually strongly dense. Okay? So we have some partial results on this, but not a full answer. So I thank you, and I stop here.